Hello friend, welcome back to Algorithm Visualized. This is Golden Sun. We are approaching the recursive solution for TOH, Tower of Hanoi. And I still have another two typical recursive examples to share with you. Today, in this video, we'll go through Fibonacci number, okay? The famous Fibonacci number 0, 1, 1 sequence, right? 2, 3, 5. So, to get a Fibonacci number in a sequence, it's defined by the sum of the previous two. So it starts from 0 and 1. So next one is 0 plus 1, right? Get this one. And next one is 1 plus 1, 2. And next one, the sum of previous two numbers, 1 plus 2 equals 3, and 5, 8. So let's calculate. Let's get the nth Fibonacci number, okay? So function Fibonacci number of n t, return an int. Excuse me. So now, what is the base case? Right? In our previous example, the base case looks like that. The base case looks like that. Here, what is the base case? Is it like that? If n equal 0, right? This the base case. So the when the zeros Fibonacci number is return 0. Okay, what is the recursion here? So the nth one is the sum of the previous two numbers. So we return Fib n minus 2, right? Plus n Fib of n minus 1. Yeah. Let's test it to make to see if it works. Test Fib, and we can xct assert equal so zeros, ones first, second, third, fourth, fifth, sixth. Okay, so 8, it should be Fib 6. Command S to save it and run. Still testing. Something might be wrong. Okay, let's stop it. Let's put a print here to see what happens here. Print n equals n. Okay, run it. Oh, you see the problem? n equals negative a huge number, it doesn't, the execution doesn't stop at n equals 0. Why? Yeah, the reason is we made two recursive call here. So for example, let's use 6 as the example, right? So when we call the fables of 6, can we go to the top? Okay, here. To get fable of 6, we need to call fable of 4, right? Yeah, to get fable of 4, yeah, don't worry about this one because we made this recursive call first. So yeah, we need to calculate that 6 minus 2 is 4. Then to calculate fable of 4, we need to calculate, right, fable of 4 minus 2. Then yeah, 2 minus 2 is 0. 0 minus 2. Oh, when we get 0 here, yeah, we hit this base case. Now it returns 0. And we still need this. We still made this recursive call, right? So when n is 0, you see, when n is 0, no, yeah, let's check this one. When n is 2, we need to calculate fable of 0 and fable of 1. That's why I have the n equals 1 here. Now here is the problem. To calculate that, to calculate the right fable of 1, because 1 is not 0, so it goes down to here. Now 1 minus 2 is negative 1. Excuse me. Here is the disaster. It is passed through and equal 0, right? And it goes down like that. Yeah, you can chase down. So how to solve that? We need to add another base case. So the base case, right, include the two conditions. If n is 1, we know the answer is, we just return 1. Now it will never, it will stop at one of the test cases. Okay, run it again. Correct, right? It passed. Yeah. So what's the next one? Next one is 5 plus 8, 13. Okay, 13. And the next one will be 21. Yeah, this one plus 13. Okay, let's add two other test cases. Equal, and the nice one. Oh no. Fable. The 7th is 13. The next one, the 8th one is 21. Fable 21. Let's see. Sorry, this is should be 8. Yeah, the 8th one. Okay. Now let's take away this one. Let's try. Let's calculate a big number. Okay. So let's comment out this to investigate that, so we can focus on something we don't know. Let's put 0 here. Fibonacci of, let's say, 20. What is the number? 20. Oh, this is not big enough. Okay, so yeah, let's keep going, because there's a performance problem of this algorithm. It's very expensive to make this kind of recursive function call. So we want to show the performance problem here. Now let's calculate the Fibonacci of about 40. One, two, three. Yeah, it takes 3 seconds, right? So the answer is that. Excuse me. 1, 2, 3. Yeah, it works. Now let's keep increasing this assert something. Fibonacci of 50. Let's count. How many seconds does it need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, I don't know when it can stop. Yeah, let's break it and think about how can we solve this performance problem. The reason is this: we duplicate a lot of calculation here. Let me show you in our whiteboard. Okay, delete that. So to calculate Fibonacci of, say, 6, right? We make 2 recursive call. We need to calculate fib of n minus 2, right? 4 and fib of 5, n minus 1, the sum of them. And to calculate the fib of 4, we need to make 2 recursive call of fib of minus 2, 2, right? Fib of 2 and fib of 3. Each one is another Fibonacci recursive call. Yeah, you'll see the problem shortly, right? Here, we need to calculate fib of 3 again here. And if you keep writing down, right, following this tree, you'll see a lot of duplication here. So the solution is we can save the result of the result instead of recalculate that, right? So we don't need to duplicate recursive calculation of that and that, right? Or this and that. We know the answer of that, the two calculations, right? The answer are same. Okay, so our solution, we can keep a dictionary here, for example. Like so we can save the answer we already know, right? So we defined our var diction. Okay, so dictionary, the data type is int to int, so equals empty. So before we make the recursive call, right, of that, we can check if we can find. So if dic of n minus 2 is not nil. If that is not nil, if it's not nil, so we we can do, let's calculate that. We define two variables, right? Like n2 int, and we are n1 int, and if it's not nil, we can find the answer inside this dictionary. We can assign n2 with dic n minus 2, right? And if dictionary n minus 1 is not nil, we can do n2 n1 equals dict. I think it's better to write this way. Sorry about the messy thing. Right? We can do that. This one equals this guy. Then if n2 is nil, we can calculate you by calling Fibonacci recursive call. So here is n minus 2, yeah. And if n1 is nil, right, we cannot find it. We can, after we get that, we need to set, right, dic n minus 2. So we updated the dictionary with n2, yeah. So here, if that one is nil, we do the calculation. Otherwise, we just use the result from the dictionary, n minus 1. And we need to update our dictionary to save the variable result of the calculation, so we don't need to do it again next time. Now here is just n2 plus n1. Hopefully it will speed up the calculation. Oh, it's, yeah, the data type should be like that because it could be nil. Yeah. Okay, so now let's test again. Sorry for the syntax problem here. Yeah, it's an empty dictionary. Oh, so because now we know it shouldn't be nil, so we can do that. Yeah. Because we already checked the nil thing. Yeah. So that the optional thing is not our focus. Yeah, it doesn't look very good, but we are, our focus here is the performance. Yeah. Run it. It's so fast. I think we get the result. Yeah. Right? So the difference is like day and night. Yeah. Yes, right? It works. So let's see how many times we make the recursive function call. And so n equals n. Excuse me. That's great. It's not too many. It's not too many. Yeah. Is there a duplication? No, right? 50, 48, 46. Now here, 1, 3, 5. Yeah. Here are, this group are odd numbers, and this group, yeah, there's no duplication. We didn't waste anything, right? And what if we, yeah, what if we comment out this one, right, and use the original solution, Fibo n minus 2 plus Fibo n minus 1. Can we print out something here? Yeah, I don't even need to continue, and I stop it. Sorry. Now let's take a look of how long, right? The list of recursive call is. You see, it keeps going. Yeah, it's a performance disaster. Yeah, it's not good. Yeah, I cannot see the end. Okay, never mind. So don't forget, right? When we write a recursive function in implementation, we need to think about the performance. Now let's put it back, the better solution. And yeah, if we put them back and test again, yeah, so it works perfectly. All the test cases passed. Okay, so thank you for watching. See you next time.